Okay, pre-cal students, in this video we will be studying polynomial functions that have a higher degree than 2. Remember the other day we studied polynomial functions that had a degree of 2. Today we're going to look at functions whose degree is higher than 2. Your heading today is polynomial functions, so please make note of that, polynomial functions, lesson 2.2, and be sure and include today's date, okay? Your heading is Polynomial Functions, Lesson 2.2, and be sure and include today's date. Now, first, we need to start off by looking at the definition of a polynomial function, okay? So here we go. Instead of giving you a word definition, I'll put an I right here. Instead of giving you a word definition, I'm going to give you a picture of what a polynomial function is. So please take really good notes, okay? Copy this down. Now, take some side notes if you need to, okay? A polynomial function, first of all, must have real integers, okay? Real integers. So, in other words, real coefficients. So all of your coefficients must be real numbers. In other words, you cannot have imaginary numbers for your coefficients, okay? Number 2, your exponents, these right here. The exponents of your variables must be 0 or greater. You cannot have negative exponents, okay? In order to have a polynomial function. So your coefficients must be real numbers, not imaginary numbers like 2i or something like that. And your exponents need to be 0 or greater. It's okay to have an exponent of 0. In fact, this negative 5 right here really has an x right here to the 0 power, because anything to the 0 power is 1. So x to the 0 power is 1. You really have negative 5 times 1, because x to the 0 power is 1, okay? So it's okay to have x's that have a power of 0, okay? You just won't usually see them, okay? And so here we go. This is not the best definition, but it's good enough for this class. You get the idea. This is a polynomial function, okay? And so, once again, your coefficients have to be real, and your exponents should be 0 or greater, alright? Now, let's continue on. So we're going to have all kinds of degrees and powers, okay? We're going to have second degree, third degree, first degree, fourth degree, etc. Types of polynomials. Next, let's take a look at polynomial graphs, and that's where we're going to spend most of our time today, is looking at tons, and I mean tons, of characteristics of polynomial graphs, okay? So you're going to write a lot, and that's why I need you guys to listen really well and take really good notes, okay? So here we go. 2 quick things to make note of. Are you ready? Number 1, please copy this down, and let's pause and make sure everyone's on the same page with me. We're now going to start talking about polynomial graphs, okay? So here we go. Number 1, polynomial graphs are continuous. Mr. Error, what do you mean by that? Well, let me show you, okay? You can copy this down or not copy it down. It's up to you, okay? Here's your y-axis. I'm not trying to be very neat, okay? And let's say you had a graph that went like this. Started here, curved, went up, and stopped right here. And then it picked up, and let's say the graph picked up here and went like this, okay? That's not a continuous graph. There's a break in the graph right there. I mean, it's really easy to see, and it's a really simple concept to understand. Polynomial graphs are continuous. This would not be the graph of a polynomial function. A polynomial function will continue. It'll be continuous, okay? Number 2, polynomial graphs make smooth, rounded turns, okay? Let me show you something about that. If I asked you to graph an absolute value function like this, you would have a V-shaped graph like this, okay? If there's a negative sign here, that's going to it'll be V-shaped, alright? Polynomial graphs will never be V-shaped. They will never take sharp, cutting turns like this so that there's a point or a vertex on the graph, okay? Polynomial graphs will always make smooth, rounded turns. Now, they might be really narrow sometimes like this, okay? That's fine, but they're going to make smooth, rounded turns, okay? So polynomial graphs are always continuous. You can take that to the bank, and by the way, rational graphs are not, and we're going to talk about those at the end of the chapter, okay? Polynomial graphs take smooth, rounded turns, alright? Okay, now, keep these two things in mind. They will help you when we start graphing polynomial functions at the end of the lesson today, alright? Also, listen to this. Knowing the end behavior of polynomial graphs is a huge help when it comes to graphing them. And you might say, well, Mr. Earhart, what is end behavior? Well, I'm glad you asked. Let me show you exactly what this is, okay? Please take really good notes. This next information I'm about to give you is really, really helpful when you start graphing polynomial functions. This is one of the most helpful things we will talk about today when it comes to characteristics of polynomial graphs. Alright, so here we go. You're going to do a lot of writing, so if the video, I would rather go too fast and have the supervising teacher pause the video than me go too slow and you're waiting, so I'm going to go fast and just have the teacher pause the video when necessary. If the degree is even and the lead coefficient is positive, then the graph will go up to the left and up to the right. Let me show you what I mean. Okay, watch this carefully, please. Let's say I have a polynomial function like this. Okay, there we go. Please copy that in your notes, students. Now, take a look at this. What is the highest exponent of the variable that you see? 4. So our degree is what? 4. Now, you might look at this and say, oh, the lead coefficient is 3 because 3 is your first coefficient. Not necessarily. You have to first write this in standard form or general form, which means you want the highest exponent first. So really, if this was written in general form, now you don't have to write it in general form, but if it was written in general form, then the 4x to the 4th power would come first, 3x cubed would come second, 2x would come third, negative 5 would be last. So in other words, the lead coefficient is the first coefficient after you've written it in general form or standard form. Some books call it both ways, okay? Now, so really you don't need to write it in this form, just as long as you know that this is your highest power. So your lead coefficient is the coefficient with that variable, okay? Or you can write it in this form if you want to, and then this number right here ends up being first. I really don't care, okay? So, what is the degree of this polynomial function? 4. What is your lead coefficient? It is what? Positive. Well, look, if your degree is even, and it is, my degree is what? 4. And the lead coefficient is positive. It is. I have a positive 4. Then the graph will go up to the left and up to the right. So what that means is this. When you're done graphing this polynomial function, it might take a couple of turns. But in the end, after it's done, now listen to me, students, in the end, after it's done making all of its turns, it will go up to the left, and it will not come down again. It will go up to the right and not come down again. Wow, Mr. Earhart, you said this is going to be really helpful. It is really helpful because in a couple minutes, we're going to learn how many curves a polynomial function can take at the most. So once those curves are fulfilled, and then you know it has to go up and go up, that really, really, really gives you a nice boundary for your graphs, okay? So let's go over this again. If the degree is even, like this one is, and if your lead coefficient is positive, like this one is, then after all the turns are done, it will go up to the left and not come down again. It will go up to let's continue on. Now, if the degree is even and the lead coefficient is negative, then the graph will go down to the left and down to the right. Okay, let me give you an example of this. Copy this in your notes, please. Please copy that in your notes. Okay, students, now, what is the degree of this function? Your degree is 2. It's your highest exponent of your variable. So you have a second degree, okay? What is the lead coefficient? Well, remember, it's the coefficient with your highest exponent, so -5, okay? Or, if you want to write this thing in general form, or standard form, this term would be first, and then -5 would be your lead coefficient, okay? However you want to look at it, but your lead coefficient is -5. So, if the degree is even, and it is, we have a 2, and the lead coefficient is negative, and we do, it's -5. Then the graph will go down to the left and down to the right. So, listen students, watch this carefully. If I were to graph this, it's going to go down to the left and down to the right. Now, polynomial functions might take a lot of turns in here, and that's fine, but when it's all said and done, if the degree is what? Even, and the lead coefficient is what? Negative, it will go down, and it won't come up again, and it will go down to the right, and not come up again. That is really, really helpful. Alright, number 3, copy this down please. If the degree is odd, and the lead coefficient is positive, then it will go down to the left, and up to the right. Copy that down please. If the degree is odd and the lead coefficient is positive, it will go down to the left and up to the right. Okay, while you're copying that down, here is a polynomial function I would like you to copy down. Please copy that down. Now while you're copying this down, please notice this polynomial function is written in standard or general form, okay? Totally and completely. Alright, so with that in mind, if I asked you what the degree was, go to the highest exponent, and we have a 5th degree. What is the lead coefficient? Well, right here. So you have a lead coefficient that is positive. Okay? So, if the degree is odd, and it is, we have an odd degree, and the lead coefficient is positive, and we have that, a +3, then the graph will go down to the left and up to the right. So, it'll go down to the left, and then I'm not sure what it's going to do in here. It can do all kinds of stuff. Then it will go up to the right, okay? I'm not sure how many turns it'll make in here. I'm just trying to say this to you. After it's made all the turns it's going to take, it will go down to the left, and it will never come up again. It will keep going down, down, down. It will go up to the right, and it will never come down again. It will keep going up, 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 okay? That is really helpful. This is when the degree is odd, and the coefficient is positive. Okay? If I'm going too fast, pause the video. Moving on, number 4, copy this down. If the degree is odd and the lead coefficient is negative, then the graph will go up to the left and down to the right. By the way, really this should be review. I mean, most Algebra 2 classes cover this, okay? When I taught an Algebra 2 course for homeschoolers, we covered this you know, all of this stuff. Okay, so hopefully this is not brand new to you guys. If the degree is odd and the lead coefficient is negative, then the graph will go up to the left and down to the right. Okay, so copy that down, please. Okay, now here's a function I'd like you to copy down. Here we go. Let's go with 2x to the, just 2x I guess, plus make that negative 7x cubed plus 5x squared minus 3. Okay, please copy that function in your notes. G of x equals 2x minus 7x cubed plus 5x squared minus 3. Okay, when you look at this, what is the degree? We'll find the highest exponent of your variables right here. So your degree is 3. Now find your lead coefficient. Well, remember, usually the lead coefficient is the number out here at the beginning, but that's only true when it's written in standard or general form. So if we were to write it in that form, this term would come first. So your lead coefficient is really negative 7. Alright? So my degree is odd, and my lead coefficient is negative. So my degree is odd 3. My lead coefficient is negative 7. So if I were to graph this, it might make all kinds of turns, but I know in the end, when it's all done making turns, it will go up to the left and it will never come down again. I'm not sure what it's going to do in here. It will go down to the right and it will never come up again. Okay, that's really, really helpful. So let's go over this again. Degrees even, coefficient positive, up and up, left, right. Degrees even, coefficient negative, down and down, left and right. Degrees odd, coefficients positive, down to the left, up to the right. Degrees odd, and then lead coefficients negative, up to the left, down to the right. You need to memorize those, not word perfect. I'm not going to have you quote them or fill in the blank or write them out on a test, but you need to know them so you can use that information to help you graph polynomial functions. Okay? Alright, moving on, here we go. Now let's turn our attention to the zeros of a function, and let's see if they can help us graph polynomial functions. Alright, here we go. Don't forget, the zeros of a function are the same as the x-intercepts of the function. So finding zeros, as you can imagine, would really, really help us. Because once we find the zeros of a function, we've really found the x-intercepts, and that's very helpful. First, the graph, boy, write this down, this is so important. First, the graph of a polynomial function will take no more turns than 1 less than the degree. Got it? The graph of a polynomial function will take no more turns. That shouldn't be here. I'm having a really good day typing, aren't I? Alright. The graph of a polynomial function will take no more turns than 1 less than the degree. Now it doesn't have to take that many terms, but at the most it will take 1 less than the degree. Copy that down, then I'm going to explain it to you a lot better, okay? Copy that down. The graph of a polynomial function will take no more turns than 1 less than the degree. Copy that down, please. Alright, now I want to show you guys something in your notes. You should have these functions written down. Go back and look in your notes. You should have this function here written down. Okay, notice the degree is 4. Do you see it? So you take 4 minus 1. You always subtract 1 from the degree. 3 is what you would get. 4 minus 1 is 3. So this graph will take no more than 3 turns. Now, listen to me, students. It does not have to take 3 turns, okay? But it won't take more than 3, okay? So it'll make 1 turn, 2 turns, or 3 turns. By the way, when as long as you keep one eye up here as you work ahead, okay? So if you want to go ahead and do the same thing for 3 and 4, that's fine, because we're going to do that. Just make sure you keep one eye up here and check your work as you go, okay? So go ahead and do it for 3 and 4 if you want. Now let's take a look here. This one, the degree is 2, so you subtract 1. 2 minus 1 is 1. So this graph will take no more than 1 turn. Hopefully you got that right, okay? I hope you went on to 3 and 4. Please do that. Go on to 3 and 4 and work ahead and see if you got them right, okay? Alright, number 3. The degree is 5, so 5 minus 1 is 4. So this graph here would take no more than 4 turns. Now, does that mean it has to take 4 turns? No, not a bit. Not a bit, okay? But it will take no more than 4 turns. Alright? Okay, hopefully you're done with number 4 already. The degree is 3, so 3 minus 1 is 2. So this graph here would take no more than 2 turns. Okay, so that's really, really helpful. Now you can look at the degree of a polynomial function and you'll know at the most how many turns it's going to take. You won't know exactly how many, but you'll know at the most how many it can take. Alright, let's continue on. Now, next, the zeros or x-intercepts of a polynomial function will never be more than the degree. Write that down, then I'll explain it. Please copy that down. The zeros, or x-intercepts, whatever you want to call them, of a polynomial function will never be more than the degree. And I'll explain that in just a second. Copy that down, please. Now, students, let me show you what I mean by this. Okay, let's go back to our 4 examples again, okay? And you're welcome to work ahead as long as you check your answers, okay? So, I look at this graph here, I know a couple things. I know the degree is 4, lead coefficient is positive, so I know it's going to go up and up to the left and right. I know it's going to take no more than 3 turns, and now I know this, it will have no more than 4 x-intercepts or zeros. There we go. How do I know that? Because the degree is 4. When you're talking about turns, students, you subtract 1 from the degree. When you're talking about zeros, you do not subtract 1. Whatever the degree is, it'll have no more than that many zeros. Now, does it have to have 4 zeros? No, not at all. But it will have no more than 4 zeros. Okay, so go ahead and take some notes, please, on numbers 2, 3, and 4 on your own, okay? I'm going to start with 2. You can work ahead, okay? Alright, here we go. When I look at number 2 here, my degree is 2, so I know this graph right here will have no more than 2 x-intercepts. Now notice, in the last problem, I used the word zeros, and here I use the word x-intercepts. I'm just doing that just to get you guys used to that. Zeros and x-intercepts are the same thing, okay? So this graph will have no more than 2 x-intercepts. Number 3, the degree is 5. So this graph here will have no more than 5 zeros. Now that doesn't mean it has to have 5 zeros, but it will have no more than 5. Number 4, the degree is 3. So this graph here will have no more than 3 x-intercepts. Okay? And of course, an x-intercept, or a zero, whatever you want to call it, is where the graph crosses the x-axis at. That's what we mean by x-intercept or 0. Okay? I hope you're getting all this, guys. Alright? So, the zeros or x-intercepts of a polynomial function will never be more than the degree. Never. Alright? Now, while we're on the topic of zeros, let's take a look at a function and find the zeros. Okay? It's important you know how to do this. So, copy this function in your notes, please. Copy this function in your notes. Let's find the zeros of this function. Let's find the zeros of this function. Okay, please listen carefully, students. You should know by now whenever you're trying to find the zeros or the x-intercepts, you put 0 in for y. So I'm going to put a 0 in for f of x or for y, and I come up with this right here. Now, the next thing I'd like to show you is we always want to try to factor whenever possible. And students, there's no way personally I want to try to factor when I have a fraction. So I'm going to multiply the entire function by 2 because my denominator is 2, and I would like to get rid of this fraction. So 2 times 0 is 0. 2 times negative 2 is negative 4x cubed. 2 times 6 is positive 12. And 2 times negative 9 over 2 would be negative 9. Alright? X. Negative 9x. Now, students, please pay attention. You should know by now, you always pull out what's common first. This should be a 2, shouldn't it? So pull out what's common. When I pull out what's common, I'm going to go ahead and pull a negative sign out too. Please let me explain why I'm pulling a negative out. In most factoring situations, you don't want the first term to be negative. It's just not normal. It helps if your first term is positive, so I'm going to pull out a negative sign. Plus, all of these terms have at least one x, so I can pull an x out. So I'm left with 4x squared minus 12x plus 9. Okay, notice I had x cubed, I took an x away. I had x squared, I took an x away. I had x, I took an x away because I pulled an x out. Notice the signs were negative, positive, negative. Now they're positive, negative, positive because I pulled a negative sign out. Does everybody see that? Now, let's factor this trinomial. Students, I warned you way back in August I was going to teach you very well how to factor, and they expect you to know it. I told you that. In pre-cal, we're not going to spend time reteaching factoring, okay? That's Algebra 1/Algebra 2, and factoring is very important. So I'm just going to go through it quickly. I'm not going to teach it. I'm just going to factor it. So I notice that I have a lead coefficient of 4. So I take my lead coefficient 4 and my constant term 9. I multiply them together. 4 times 9 is a positive 36. And so because we have a positive 36 here, we're saying to ourselves, what two numbers when multiplied together give you 36? When add together would give you a negative 12. Well, I'm thinking of, let's see, negative 6, negative 6. When you multiply those two, you get positive 36. And when you add them, you get a negative 12. So remember what to do. We write our first term, 4x squared. We write our last term, positive 9. And right in the middle, we're going to put negative 6x, negative 6x. Okay? Now, I'm kind of running out of room here. Pull out what's common in the first two terms, which would be 2 into x. 2 goes into 4 and 6, and you can take 1x out of both of these, and you're left with 2x minus 3, okay? Over here, because the first term's negative, pull out a negative, 3 goes into both of those, and you should be left over with 2x minus 3. Now students, just check your work, okay? 2x times 2x, 4x squared. 2x times negative 3, negative 6x. Negative 3 times 2x, negative 6x. Negative 3 times negative 3, positive 9. This parentheses here and this parentheses here should match. If they don't, you've messed up somewhere, okay? So here's what I have. See this negative x? Put your negative x right here. Got it? Then you write your matching parentheses once. Check off my negative x. Write your matching parentheses once. All of this should look familiar, guys. And you're left over with this and this, 2x minus 3. Okay, So take each group and set each group equal to 0 in order to find your zeros, okay? So take negative x, set it equal to 0, divide by negative 1, x equals 0. So there's 1 0 right there, alright? Now, take 2x minus 3, set it equal to 0 and solve. Bring your 3 over, make it positive. Divide by 2, and you get 1.5 or 1.5. And by the way, notice this parentheses here is identical to this parentheses here, so there's no need to take this parentheses and also set it equal to 0. There's no need, because you'll get the same thing. So there you go. Your x-intercepts are 0 and 1.5. That's really helpful when you start graphing this thing, okay? So I just wanted to go over how to find those zeros, okay? It's really important how to do that, alright? Now, I want to talk about the topic of multiplicity, okay? Because if you'll look back here, notice all of your factors were linear. Whoa, Mr. Arrow, what are you talking about? Let me show you. Listen to me, please, students. Zone in. Pay attention. All of these factors were linear because what is the power of your x? 1. That's linear. What is the power of your x? 1. That's linear. What is the power of your x? 1. That's linear. This is a factor. This is a factor. This is a factor. That's why it's called factoring. You're breaking the expression up into factors, so we call it factoring. So notice all of your factors here are linear factors. Got it? Notice we had multiplicity. Multiplicity, yeah. We had 2 parentheses that were identical. Okay? So we had a multiplicity of 2 because there were 2 parentheses. Now if there would have been another parentheses in this, 2x minus 3, then the multiplicity would be 3. This 0 right here, 1.5, would have a multiplicity of 3. Does that make sense? Because you have 3 parentheses that give you the same 0. Okay, Mr. Aaron, I get it. That's fine. Why does that matter? Well, I'm going to show you right now why that matters, okay? But I want to first of all show you what I meant by multiplicity, okay? Now, here's the deal. Let's discuss the topic of multiplicity. Watch this carefully. Hold on one second. Sometimes I forget how much I've typed and how much I'm going to say on my own. So I have to think about that. Okay, let me show you what I mean by multiplicity. Let's write down a really long make-believe function, okay? Just humor me and write this down, okay? Let me get a drink here real quick. Okay, here we go. Now, copy this down. X plus 3. Let's pretend we had a really huge function and we graphed it, or we factored it to find all the zeros, okay? Make a little space here, guys, and I want you to put x squared right here. X squared, then x plus 3, x plus 1, x plus 3, 2x plus 1, 2x plus 1, x minus 1, 2x plus 1, 2x plus 1. Okay, I'm going to give you just a second to copy that down. Please copy down that really, really long factored polynomial function. It's all factored for you, okay? And just kind of hope and pray that I never give you one of these on a test, okay, to factor. Hope that it's already factored for you. That'd be really difficult to factor that if it wasn't already factored. Okay, here we go. If you're still copying it down, that's okay, you'll catch up. Now, let's go through each one of these, and I want to show you something you need to see. Now, notice for your x minus, well, first of all, let's go to each parentheses. Let's pretend we set this equal to 0 and solved. What would your 0 be? Negative 3. Pretend you took this parentheses, set it equal to 0 and solved like this. Bring the 1 over, make it a positive 1. What would your 0 be? 1. What would your 0 be here? Negative 3. This is a little harder to do in your head, but trust me, it'd be a negative 1/2, okay? This would be a negative 1/2. This would be a positive 1. This would be a negative 1/2. Now, watch what I do. This is so cool. I know for a fact I have x-intercepts at all these numbers, correct? So I have an x-intercept at -3. Please take really good notes. Copy all this down, please, guys. Please take good notes. I have an x-intercept at 1. I have an x-intercept at -3. I already marked that. I have an x-intercept at -1/2. So right here. X-intercept at 1 and -1/2. Now, I want to show you something that's really, really important. Now you write this in whatever words you want to write it down, and probably if I was a perfect teacher I would have had this typed for you in a sentence, but I didn't. So write this down however you feel helps you best remember this, okay? Whenever the multiplicity is even, whenever the multiplicity is even, you have a tangent. Now I'm gonna explain all of this in a second, guys. I'm gonna explain it really well. Just take notes right now. Whenever the multiplicity is even, you're gonna have a tangent for at the x-intercept. So a tangent at the x-axis or the x-intercept. Okay. And whenever your multiplicity is odd, and again, I'm going to explain all of this to you really, really, really well. I should have had these two black sentences here that I'm writing up with my pen. I should have had those typed for you in sentences, and I apologize for not doing that. If your multiplicity is odd, then your x-intercept is not tangent. X-intercept is not tangent. Now, are you ready? Here we go. Look at your -3. How many -3s do you have? 1, 2, 2. So the multiplicity, your -3, has the multiplicity of what? 2. Okay? 2 is what? Even. So that means at this x-intercept, -3, the graph's going to be tangent to the x-intercept. And I'll show you what that means in a second. But let's go over this again. How many -3s do I have up here? 2. So what's the multiplicity of my -3? 2. Is 2 even or odd? Even. When your multiplicity is even, then you're going to have a tangent at that x-intercept. Now, what does tangent mean? It means this. The graph is going to hit right here and then shoot back up again. Or if it's down here, that means it's going to hit and then shoot back down. So in other words, I know for sure at -3, the graph is not going to do this. The graph is not going to hit -3 and continue going down like this and then come back up. It's not going to do that. It will not do that. Okay? It's going to either hit and go back up like this, or it's going to hit from down here and go back down. That's what tangent means. Okay? Now, look at your 1. What is the multiplicity of your 1? Well, let's see. 1, 2. So that means the graph, the multiplicity of 1 is 2. 2's even. So that means the graph is going to hit here at 1. It's either going to hit and go back up again, or if it's down here below, it's going to hit and go back down again. Isn't that cool? That's really cool, guys. That's helpful to know. Okay? What about the multiplicity of your -1/2? 1, 2, 3. The multiplicity of my -1/2 is 3. That is odd. So that means it will, the x-intercept will not be tangent to the x-axis. So we know the graph is either going to hit it like this and keep going through, or it might go up like this. But we know for sure it's going to pass through the x-axis and continue to go. Now, guys, I hope that makes sense. If the multiplicity is even, it's going to hit the x-axis and bounce back down or bounce back up, depending where the graph is. If the multiplicity is odd, then the graph is going to pass through the x-axis. Okay? Now, I gave this problem for a reason. I was trying to trick you guys, and maybe I did, maybe I didn't. If I was there in class, I would say to you guys, okay, we're done. Does anybody else see anything else? And I would kind of wait to see if anybody sees anything. Remember way back here earlier, these factors were linear. Remember that? Okay, well look at our factoring. Are all of our factors linear? Booyah, not this one. That's x squared. So you know what that means? You really, if you want to check, now listen to me guys, if you want to check the multiplicity of all of your x-intercepts, you must make sure that all of your factors are linear, and this is not linear, this is x squared. So how am I going to fix that? Well, instead of putting x squared, I'm just going to put xx, like this. xx. There we go. Now, here's the problem with that. I've got a 0 of 0 right here. Look, if I take this group right here, x, and set it equal to 0 and solve, what is my 0 for this group? 0. What's my 0 for x? 0. It is, Mr. Hart. Well, sure it is, guys. Any group that has an x has to be set equal to 0. So if you take this x right here and set equal to 0, you just get 0. And if you take this x right here and set equal to 0, you just get 0. So we've got another x-intercept. I wish I was there in class to see if some of you would have caught that on your own. So we have another x-intercept. It's 0. So I'm going to put that right here. And those are the ones right there that students quite often miss on a test or a quiz. So always check your factors and make sure they're all linear, okay? Now, we have an x-intercept of 0. What's the multiplicity of my 0? 2. So I know the graph is going to hit 0 and bounce back up, or it's going to hit 0 and bounce back down, because the multiplicity is 2, which of course is even. I hope I explained that well. Here's a picture of it. Now, you do not have to write this in your notes, but you're welcome to if you want to. That's totally up to you, okay? There it is. Okay, if you were to factor this expression right here, I'm going to factor it for you very quickly, okay? Y equals negative 2x to the 4th plus 2x squared. Now watch. First of all, my first term's negative, so pull out a negative. Second of all, they both have a 2, so pull out a 2. Third of all, I've got an x squared. I can pull out of both of these. So I'm left with 2. I'm left with x squared minus 1. Now let's see if that's right, okay? Negative times a positive is negative. 2x squared times x squared is 2x to the 4th. Negative times a negative is positive. 2x squared times 1 is 2x squared. Now I can factor this again. We've learned how to do that, okay? Negative 2x squared. We know the square root of this term. We know the square root of this term. And so we have the difference of perfect squares. So the square root of x squared is x. So put an x here and here. The square root of 1 is 1. Put a 1 here and here. Make one positive, make one negative. We learned all of that the first week of school when we were factoring, okay? So, do I have linear? Are all of my factors here linear? No, they are not. Look at my 2x squared. That's a power of 2. So I'm going to put negative 2, x plus 1, x minus 1. Now, are all of my factors linear? Yes. Power of 1, power of 1, power of 1, power of 1. For this x right here, I would have a 0 of 0. For this x here, I would have a 0 of 0. For this group here, I would have a 0 of negative 1. For this group here, if I set it equal to 0 and solved, I would have a 0 of positive 1. So that means I have x-intercepts at negative 1, 0, positive 1. Now, what's the multiplicity of my 1? Well, there's just one of them. That's odd, so it goes through the axis. What's the multiplicity of my negative 1? Well, there's just one of them, so the multiplicity of my negative 1 is 1. That's odd, so that means it's going to go through the graph at negative 1. What's the multiplicity of my zeros? Well, there's 2 of them. That's even, so notice how it hits the graph here and then goes back up again, okay? Alright, that's what we're talking about when we say multiplicity. Alright, now I'm going to quickly go back to some different slides and quickly review what we've talked about today. Okay, first of all, we talked about polynomial graphs are continuous and they make smooth rounded turns. Okay, next we talked about the end behavior, the degrees even, lead coefficients positive, degrees even, lead coefficients negative, etc., etc. I'm not going to read all of this to you, but we talked about end behavior of a graph. Know that it's important. Okay, we also talked about this right here, that We talked about that. So if you have a fourth degree polynomial function, it will take no more than 3 turns. Okay, we talked about that. Then we talked about the zeros or x-intercepts will never be more than a degree. So if you have a third degree function, there will be no more than, that's really good handwriting, no more than 3 zeros. Okay, we talked about that. Then we talked about multiplicity. Okay, even multiplicity, the x-intercept is going to be tangent. The graph will be tangent to the x-axis there. If the multiplicity is odd, then the graph will go through the x-axis at that point. Alright, and so we've learned all of these tips to help us graph polynomial functions right. So let's graph them. Here we go. Let's graph 1, 2, and then we're done with the lesson, okay? So here we go. Let's start off with this one here. Let's see if we can't get some tips going. First of all, let's write some stuff down. Are you ready? What is my degree? Good job, you're exactly right. 4. What is my lead coefficient? Positive 3. So I will add turns will be less than or equal to, well, you take the degree, you subtract 1 from the degree, that would be 3. So the turns will be less than or equal to 3, okay? How about the zeros? The zeros will be less than or equal to, what's my degree? 4. So 4. So I know it'll take no more than 3 turns. I know it'll have no more than 4 zeros. Now, how about the end behavior? My degree is even. My lead coefficient is positive. So I know it's going to go up to the left. And I know it's going to go up to the right. Okay? Man, we're doing great, guys. All that we have to do now is just find the zeros. So let's find the zeros of this. First of all, let's factor out what's common. You have a 3 and a 4. There's really nothing that goes into 3 and 4 evenly. However, you can pull out x cubed. So pull out x cubed, and you're left with 3x minus 4. Alright? Now, let's check our multiplicity, okay? I have x cubed, so that's really x, 3x minus 4. Okay? Now, trust me, guys, if you take this and set it equal to 0, you'll get a positive 1 1/3, okay? And over here, of course, this group would give you 0 for a 0, this group would give you 0, and this group 0. So my multiplicity of my 1 1/3 is 1. That's odd. The multiplicity of my 0 is 3. That's odd. So I know I have x-intercept at 0 and an x-intercept at positive 1 1/3. Now, I'm just going to go ahead and put a little line. If it was tangent, I'd make a note like this so I wouldn't forget that, okay? Or a note like this so I wouldn't forget that. But it's not tangent, so I'm going to put a little line here and a little line here so that I remember it is going to go through the graph, okay? Alright, now, having done all of this, there's really not a lot more I can do except draw my table of values, okay? Now, let's use some good old common horse sense. Are you ready? Okay. We know the graph's going to go up. Okay. We know it's going to hit here and it's going to have to curve and go back up again. So we know that for a fact. Are you all with me? Watch this. We know. Well, actually, let me take that back. I don't know that because, let me show you something real quick here. The graph could be coming down here and turning and going back up. Of course, actually, I don't have any more x-intercepts over here. So, there's no way the graph's going to be going down over here. Now, please watch, students. If the graph's going down like this, listen to me, guys. Is it not going to have to curve back up again to go up? Yes, it is. And then it's going to hit the x-axis. And we know I don't have any x-intercepts over here. That's impossible. Do you see how you can use common sense and just think through this? So I know for sure the graph here is going to be going through this way here. Okay? Now, what I'm going to do quickly is I'm going to plot some points to the left of my 0. This is my last 0 to the left. So I'm going to plot -1, -2, -3. Just kind of see what it does. Okay, so -3, -2, -1. 1. So put a negative 3 in. I'm going to grab my calculator real quick here. That's going to help me. And by the way, can I make a suggestion to you? I would enter this into your calculator at your y equals button, top left, because once you enter this into your grapher, you can then scroll over to your table of values. So I'm pushing y equals, and I'm typing this whole function into my grapher. So 3x arrow 4, 3x to the 4th power minus 4x arrow 3. And I'm going to go to my table of values, okay? So for negative 3, I'm going to get 351. For negative 2, I'm going to get 80. And for negative 1, 7, okay? So that's a pretty good idea, guys. Negative 3, you're way up here. Negative 2, you're at 80, and negative 1, you're at 7. So 1, 2, 3, 4, 5, 6, 7. So it's shooting up pretty quickly, is what I'm trying to show you, okay? So it's going to hit here. Now when it hits here, remember if the multiplicity would have been even, then we'd know it curves back up again right here. But the multiplicity wasn't even, so we know for sure the graph goes through. So I'm going to try 1, positive 1. Positive 1 gives me negative 1 right here, okay? So more than likely I'm thinking it hits here, probably comes below this, and then goes back up again. So what's the only way to know what it does right here? I'm going to put in a half. I'm going to put in 1/2 into my grapher, okay? Now let me tell you how to do that. Are you listening carefully? Hit second trace, or in other words, second calculation. Trace is the top row of buttons, 4th one over from the left. Hit second trace, and then option number 1 says value. Hit enter on value, okay? Then after you've done that, it's going to say x equals on the bottom left. Type in 0.5 and hit enter. Okay, there you go. Negative 0.3. So at 0.5, you're at negative 0.3. Alright? So I was wrong in what I thought it was going to do. So at least I'm being consistent. I'm being wrong a lot today. Alright, so at a half, we're at 0.3. So it looks like it's going to come here and hit, and then kind of goes quickly around it and go up like that. And that's good enough, guys. I'm not asking for anything to be perfect. Now, students, I know this graph can take at the most how many turns? 3. But I know it's not. I know it's got to go up, okay? Now, it could do this. It could do that. It might do something like that, okay? But it will not cross the x-axis again. So we're going to make sure that everything's legit here. We're going to put what numbers into our table of values? 2, 3, 4, maybe 5, okay? So 2, 3, 4, 5. And now using my table of values in my calculator, which takes no time at all. 2 gives you 16, 3 gives you 135, 4 gives you 512, and 5 gives you 1,375. So I think it's a pretty good bet. It's pretty safe to say that at 2, we're way up at 16. It's going up, and it's staying up, okay? It's not coming down again. There we go. So we graphed a polynomial function, okay? And we used all of this information. We knew how many turns it could take at the most, how many zeros at the most. We knew about multiplicity. We found our zeros. The zeros are very helpful, guys. When you find the zeros or the x-intercepts, you can then plot points to the left of the last zero, in between your zeros, to the right of this zero over here. You can do all of that and get a really good picture of the graph, okay? Feel free to work ahead on this one, or you can stay with me, okay? Now, before you start to factor this, I do want to show you one thing, then you can work ahead. We already factored this earlier, okay? Or I thought we did. There it is right here. Okay, we already factored this, and here it is right here. I'm gonna cut and paste this, okay? So let's not factor it again, okay? We already factored this once, and once is enough, okay? So here we go. Let's go ahead and put that over here. excuse me, if we were to factor this, we'd get this right here, okay? But first of all, let's go back over here. What's my degree? 3. Okay, so I know the terms. The terms will be less than or equal to 2. Always 1 less than degree. The zeros will be less than or equal to 3 because the degree is 3. Okay, now my lead coefficient is -2. Lead coefficient is -2. So I have an odd degree and a negative lead coefficient. What does that mean? Do you remember? Look in your notes if you need to. Odd degree, lead coefficient's negative, okay? That means I'm going up to the left and I'm going down to the right, okay? Look in your notes and you'll see that, okay? Now, multiplicity. I do have multiplicity here of 2. Right here for this x, my 0 would be 0. For this group, my 0 would be 1 and 1/2. And for this group here, my 0 would be 1 and 1/2, okay? So there's my x-intercepts. So let's come over here and plot those. 0 is 1 x-intercept and 1 and 1/2. Now remember, at 1 and 1/2, we're going to hit and bounce back down. Okay, please don't forget that. Alright, let's go ahead and plot some points to the left of this 0. -1, -2, -3. I guess we can do that right here. We have plenty of room right here. So -1, -2, -3. Okay. Now, I'm going to go ahead and type this equation right here, this function, into my grapher. Let me clear out the old equation. And here we go. -2 x to the 3rd power plus 6x squared minus, I'm going to put 9/2 in parentheses. And then x. Okay, so -2x arrow 3 plus 6x squared, then minus, in parentheses, 9 divided by 2. Close your parentheses and then put x, okay? Now my table of values is going to be, let's see. For -1, I'm going to get 12.5. For -2, 49. And for -3, 121.5. So guys, it's looking pretty safe to say -1 is all the way up here at 12 somewhere. It's shooting up really, really quickly. Okay? And it's hitting here. Now, what is the multiplicity of my 0? Wasn't my multiplicity of 0 just 1? So I know the graph's going to cross through here, okay? I know that for a fact. So I want to kind of see what the graph's doing in between these two numbers. So I'm going to put in 1/2 and then 1. Alright? Now 1 is on my table of values. 1 gives you out a -1/2. Okay? So 1 is -1/2. Now, 1/2 would be, let me hit second trace or second calculate, enter on value, option number 1, and then type in 0.5. 0.5, and you get out -1. Alright, so you're over 1/2, you're down to -1, okay? So it looks like the graph's going to hit here. Hit here. Now look, remember, at this here, the multiplicity was even, so we know it's going to hit here and come back down, okay? So it hits here and it starts coming back down again. So I would like to put in 2, 3, and 4 into my table of values. So 2 on your table of values gives you out a -1. 3, -13.5. And 4 is -50. So it's looking like it's going to keep shooting down, okay? So at 2 it's -1. At 3 it's way down here at -13. So there we go. Now students, I would like to show you something, okay? This thing can only take how many turns at the most? 2. So it's already taken 1, 2. So I know there's no way it's going to do any more dip-de-doos, come up like this and then go down. It's not going to happen. And I know it has to keep going down because of my end behavior. Same thing here. I know this thing's not going to do any tricks like this because that'd be more turns, and we've already used our 2 turns. tell you how many turns it's going to take it the most. If you factor it and find the zeros, your x-intercepts or your zeros are especially helpful when it comes to graphing the polynomial, because guys, you can then know which points to put in your table of values. Go left of the zero, in between your zeros, to the right of your zeros plus. The multiplicity is also very helpful. Okay, alright, that's it guys. I hope this video has been a help to you. If you have any questions, don't hesitate to call or